Hello, welcome to Algebra 2 Common Core. Today we're going to work on Lesson 3, Graphs of Logarithms. So in this lesson, we will learn how to make graphs of logarithms by doing the inverse of an exponential function, and then we'll talk about some of the aspects of the construction, including transformations, domains, ranges, and even asymptotes on our graph. Let's start with exercise number 1, where we're going to learn how to do the graph of the logarithmic function y equals log to the base 3 of x. It, of course, is the inverse of y equals 3 to the x. They are inverses of each other. So let's start by making the table of values for the graph y equals 3 to the x. Remember that 3 to the negative 2 power gives us 1/9. 3 to the negative 1 gives me 1/3. 3 to the 0 is 1, 3 to the first is 3, and 3 to the second is 9. Now I'm going to go ahead and plot those points on my graph. If you would go ahead and do that also, and then come back and we'll compare. So the blue graph is a graph of y equals 3 to the x. We recognize this as an exponential growth graph because its base is bigger than 1. Now if we go ahead and graph the inverse of this, remember that the inverse means that we are going to reflect this graph over the line y equals x. So that's the transformation, a reflection, where I just switch the x and the y coordinates from my original table of values. So let's fill in those values. Instead of negative 2 1/9, I'm going to have 1/9 negative 2. And so on down the list, reversing the x and the y coordinates to get the table of values for the inverse, which is y equals log to the base 3 of x. Let's plot those points and compare and graph and come back and compare notes. So I graphed the red function y equals log to the base 3 of x. You'll notice that this graph is the reflection of the blue graph over the diagonal line y equals x. So the red graph is the inverse of the blue, and the blue is the inverse of the red. I've labeled both of them as well. Let's talk about the domain and range for each of those. The domain of the exponential function should be all real numbers, so I'm going to write it in interval notation as negative infinity to infinity. The range for the exponential function should be everything above 0, so again I'm going to write it in interval notation as 0 to infinity. For the red graph, the log has a domain. If you take a look carefully at that, I see that every single x value has to be bigger than 0. So the domain is 0 to infinity, and the range is all real numbers, so that's negative infinity to infinity. So you'll notice that when we took an inverse, what has happened is the domain of the exponential became the range of the log, and the range of the exponential became the domain of the log. That makes sense because we've switched the x and the y coordinates in our equation, so the domain and range should switch as well. Now let's look at the graph of a log without having graphed the exponential first. I am, though, going to make the table of values for the exponential. So my exponential equation is y equals 10 to the x. So I'm going to start out by saying when x is negative 2, then that tells me that y is equal to 1/100th, 10 to the negative 2 power. When x is negative 1, y would be 1/10. When x is 0, y is 1. When x is 1, y is 10 to the first power. And when x is 2, then y is 10 to the second power, which is 100. Now, when I'm not going to plot those points. Instead, I'm going to reverse the x and the y coordinates. In my log equation, it's going to be y is equal to log to the base 10 of x. So reversing these two, let me do this in red this time. I'm going to say the x is going to be 1/100th, so the y will be negative 2. The x is 1/10 when the y is negative 1. The x is 1 when the y is 0. The x is 10 when y is 1, and x is 100 when y is 2. So on the graph, I'm not going to be able to plot all of these, but I'm going to, on my axes, divide this up. I've got that the axes go up to 10, so I'm going to call this 5, and then make intervals in between. Same thing between 5 and 10. So I've got those numbers right there. So graphing the log function, I see that I'm going to cross over the x-axis at the point 1, 0. And at the x value of 10, I know that my answer is going to turn out to be 1. For the fractional x values, I see that I get a negative answer for my y. So my graph is going to look something like this. And this is going to be the graph of y equals log to the base 10 of x. Now you'll notice that this graph does cross over the x-axis. Its x-intercept is going to be the point 1, 0, but it doesn't cross over the y-axis. In fact, the y-axis is another important thing for this graph. It's an asymptote. You'll recall that we saw an asymptote on an exponential function, but on the exponential function, the asymptote was the horizontal line y equals 0. This asymptote for our log graph is going to be the vertical line x equals 0. So this line right here, the y-axis, my graph is getting closer and closer to, but it's never going to touch it. So we can also then tell what our domain and range are. For the domain, I know that I'm starting at 0 and going to infinity. And for the range, I know that it's all real values, so from negative infinity to infinity. Now the graphs that we have taken a look at so far are basic log graphs. But of course it's going to be helpful to us if we're able to do some transformations on these graphs. So we're going to look at some shifting of graphs, just like we looked at shifting of exponential functions. So looking at our first equation, y equals log to the base 2 of x minus 4. Because I see that my x is being affected, that tells me that I'm going to have a horizontal movement. Now you'll recall from the last few lessons that when we did exponential graphs, if the x had a subtraction with it, we had to think of the opposite direction. So in this case, log to the base 2 of x minus 4 really means that we are going to take this graph and shift it 4 units to the right. And again, we're looking at the x value and we see that the x is being adjusted. Let's try number 4. Y equals log to the base 3 of x plus 1 plus 2. I've got two transformations that are happening in this case. X has a 1 added to it, but then the whole function has a 2 added to it. So we've got to think of these two differently. First of all, let's look at the x. So I see that what's going to happen is my graph is going to shift 1 unit. And again, we think about it with the opposite sign, so it's going to be 1 unit left. When we're going in the vertical direction, though, this plus 2 is affecting my whole y coordinate. So if I add 2 to my y coordinate, I'm also going to shift 2 units up. For number 5, I see that this log has an x minus 2 as its argument, and then we're going to subtract 3. So for the x minus 2 portion, we see that we are going to do a shift of 2 to the right. And then for the minus 3 portion, we see that we're going to shift 3 units down. You'll notice that it didn't matter what the base of the log was. In each case, the base was different, but the shift is not affected by that base. Let's apply what we've just learned about transformations of log functions and see if we can tell which of the equations is the correct one for this graph. Now, first of all, we saw that on a regular log graph, we had a vertical asymptote at the y-axis. So our vertical asymptote would normally be right here. But this shows a graph that's going to the left of that y-axis. If we count over, we see that it's going 3 units to the left. So I know that my equation must have a log in it that has an argument of x plus 3 to accommodate for that 3 units to the left. So automatically I know that I am going to eliminate choice number 1 and choice number 2 because they don't have the argument of x plus 3, signifying a left shift of 3. Now the decision is this a base of 2 on my log or is it a base of 3? That's going to require me to take a look at some of the ordered pairs that have to accommodate this graph. So when I look at this graph, I see that some of the ordered pairs that are on the graph, if I count it out, I see the point -3, -3. I also see the point, oh, I'm sorry, that's not quite -3, -3. So let's erase that one because I know that my asymptote has to be at -3. So I'm not going to have that point. It's going to get close to -3. Let's look for points that I know for sure are on the graph. So for example, this point right here, I know to be -2, -1. The point right next to it, the x-intercept, is the point -1, 0. I also know that the point 1, 1 is on this graph, and if I count carefully, I see that the point 5, 2 is on this graph. So when I plug into the remaining 2 choices, I'm going to try a couple of these points. So for example, if I try the point -1, 0, plugging into choice number 3, I would have y is equal to log to the base 2. If I'm using the point -1, 0, -1 plus 3 is 2, and then I'm going to subtract 1. And when I calculate this, log to the base 2 of 2 just means what's the exponent that 2 has to be raised to give me a 2? And that answer is 1. So the answer for this log, when I subtract 1 minus 1, that gives me an answer of 0. And I see that yes, indeed, -1, 0 is on the graph that I'm looking for. If I try that point over here, y equals log to the base 3 of -1 plus 3 is 2. I don't know what number I have to raise 3 to get an answer of 2. So clearly this choice is not giving me the ordered pair -1, 0. Now I could have tried any ordered pair, but the intercept there gave me a nice value to work with. So I know that choice number 3 is the right equation for this graph. When we talk about log functions, it's especially important to discuss the domain of a log function. Usually we said that our log function is going to be to the right of the y-axis. So usually my log function domain is going to be from 0 to infinity, not counting 0. That means that whatever my argument is has to be a positive value. So when I'm given a function that's a log that has been transformed or shifted, to find the domain of the log function, I'm going to have to make sure that the argument, the thing that I'm taking the log of, has to be greater than 0. Now you'll notice that I'm not including 0 because x equals 0 is a vertical asymptote for that graph. So for example, if I want to find the domain for number 7, I'm going to take the argument 2x minus 6 and say that that value, 2x minus 6, has to be a number that's greater than 0. When I solve this for x, I get 2x is greater than 6, so x must be greater than 3. So in interval notation, this domain would start at 3 but not include 3 and go to infinity. For exercise number 8, again I'm going to take a look at the argument. The vertical shift does not change my domain, that would change my range. So I only want to look at the part that is being affected by x. So 3x minus 4 has to be greater than 0. Therefore 3x is greater than 4. So when I divide by 3, x is greater than 4/3. Again, in interval notation, I would write this as 4/3 to infinity, not including 4/3. For the last example, I've got y equals log to the base 5 of x plus 2, so I'm going to look at that part of the argument. X plus 2 has to be greater than 0. Therefore, x is greater than -2, so my domain is going to be from -2 to infinity. So finding domain is going to be very important for us because if I put these functions into my graphing calculator, I'm going to have to know what values of x will give me outputs. So these are the values of x for which the log has an output. And it is completely dependent on whether I've shifted my log function in the horizontal direction. For number 10, let's go ahead and do a graph where we're going to see a shift. So I'm going to start with the first graph, f of x equals log to the base 2 of x. When I graph that, I'm going to start with a basic table where I do my exponential first. So as an exponential, this would be 2. If I rewrite this, I'm going to start with the inverse. So y equals 2 to the x. So y equals 2 to the x, if I plug in values for x, -1, 0, 1, and 2. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. But that's the table for the exponential function. So to find the log, I'm going to do the inverse, and I'm going to make that in blue. So I'm going to have 1/2 -1, 1, 0, 2, 1, 4, 2. So this graph at 1/2, I'll go to -1. At 1, I'll go to 0. That makes sense because my log graph normally crosses the x-axis at x equals 1. 2, 1, 4, 2. I could have put one more point on here. If I raise 2 to the third power, that gives me 8. So the point on my graph would be 8, 3. So that looks something like that. So this graph is the graph of y equals log to the base 2 of x. Now notice the second graph that I want to make. G of x equals log to the base 2 of x plus 2. So if I just know what the transformation is, I can take each point and do that transformation. So reading that, I can tell that this is going to be a shift of 2 units to the left. So I'm going to take every single point and count over 2 spots, 2 units. So I've moved that one over 2 to the left. 1, 0 moves over to -1, 0. 2, 1 moves to 0, 1. 4, 2 moves over to 2, 2. And 8, 3 moves over to 6, 3. So I'm taking the blue graph and I'm shifting it 2 units to the left, and that gives me the graph of y equals log to the base 2 of x plus 2. So the transformation, I guess I could have written it underneath here, transformation was shift 2 to the left. Now we want to algebraically find the x and the y-intercept for this function. So I'm going to go back to my equation. G of x is equal to log to the base 2 of x plus 2. So for the y-intercept, that means that I want to make x equal to 0. So I want to find g of 0. That's just going to be log to the base 2 of 0 plus 2, which of course is log to the base 2 of 2, which asks the question, what exponent do I need to raise 2 to get an answer of 2? And that answer is 1. So my y-intercept is the point 0, 1. I can definitely see that on my graph right here. Now let's go ahead and find my x-intercept. The x-intercept is when I make y be 0. So another way of writing that is the g of x would have to be 0. Let's set my equation log to the base 2 of x plus 2 equal to 0. Remember how we solve a log equation? We can rewrite this as an exponential. Use your arrows if you'd like. So we're going to write 2 to the 0 is equal to x plus 2. 2 to the 0 equals x plus 2 allows us to solve 1 equals x plus 2. So therefore x is equal to negative 1. This tells me that my x-intercept is the point negative 1, 0. And again, if I look at my graph, I can definitely tell that that point is right here where the graph crosses the x-axis. We've done some great graphing today. In class, we'll continue with our graphing, finding domains, finding ranges, x and y intercepts, and of course, asymptotes. So please make sure that you're familiar with all of these concepts for class. Have a great night, and we'll see you next time. Bye-bye.